Welcome back. So in the previous video, we've just had a look at breadth first search, BFS, and we've seen that it is both complete and optimal, right? It's able to find the shallowest goal node in our tree, and therefore it always guarantees to return the optimal solution. Now, what was important to note is in that video, we had an asterisk next to completeness and optimality based on whether or not the depth of the solution in the tree, so the depth of any node in the tree, is correlated or directly related to the actual cost of the edge, the cost of the actions. Now, that is not always the case, and that's going to lead us into today's video, which is on uniform cost search, UCS, which is the next fundamental step in our search algorithm journey. So, the difference is that in real-world problems, things don't always have the same cost. Certain actions can be more expensive than others, maybe different paths have different lengths, and so when we look at a graph like this in our search tree, essentially you'll see that there are going to be edges, actions, that cost different amounts. And so we're going to have a quick look at that. So let's throw in some random numbers over here, and we're going to work with this moving forward. So in problems that do have edge costs, of course we know that we're going to have to reason over these differently and inform the order of nodes that we expand based on the additional information that we have in the problem. So that is where uniform cost search steps in. Our search strategy here is that we're going to expand nodes in order of lowest path cost. Okay, we often describe the path cost in terms of the generic expression g of n. This is just a natural convention. This does not have to be the case, but it's something you'll constantly see all the time, and we'll interact with this in further videos. So what we're saying is for some random node n, any node n in our graph, it has a cost of the path so far in order to reach this node. So here let's consider the example that we're looking for the gold node g. So the path cost to g is of course going to begin at the root. It's going to follow the edge to c, which has a cost of 2, and then follow the next edge to g. So the path cost g of the goal is going to be 6 in this situation. And so if we remember from BFS, there the search strategy in terms of the data structure, its actual implementation, it was a first in, first out queue. Well, the difference here is that UCS is going to maintain a sorted list based on g of n, okay? So what ends up happening then is the equivalent data structure is what we call a priority queue, okay? So as nodes are generated and added to the open list, they are going to be sorted and placed in their correct respective position based on their path cost. So that's why, slightly different to BFS as we just saw, where we just had the root node A at the beginning. So I've written this slightly different. I'm saying, hey, we begin with the root node A, which has a path cost so far of 0. Because of course, we have not yet had to have an action, we've not yet followed an edge with an associated action cost. Okay, so let's have a look then at exploring the behavior of UCS on this little example here. So of course, in the first step, we are going to be expanding the root node A. So we're going to pop that from our priority queue, from our open list, and we're going to generate its children. So here we find both B and C, and we're going to add them with their respective costs. We have to find that B has the smaller cost, and therefore we have to add that first. It has a cost of 1. We also find C with a cost of 2. Okay, so in the next step then, we are going to expand B next. So we pop that out, and we're going to generate its children. So we find now D and E. Okay, so we find D with a cost so far of 5 plus 1. So D has a cost of 6, and E has a cost of 11. We also previously had the node C with a cost of 2 that still exists. So we would insert D and E into the open list with their respective costs, but C has the best cost, the best path cost so far, so that remains at the front of the queue. Now we add in both D and E, but these are ranked according to their G of n. So for D, that is going to be 6. And for E, that is 11, which is far from exciting. So then the next step is, of course, we are going to move on and expand node C. Okay? What this means is we find its children now, F and G. We add both of these to the open list. But now we have some interesting dynamics in terms of the costs that we need to sort out. So node F is being added with a cost of 4. Node G is being added with a cost of 6. Okay, so F is now the most promising. F of 4 goes right into the front of the open list. Next, we have that we see that actually both G and D both have a cost of 6. This is where we again enter into tie breaking. So you can choose to sort this either way. You can use rule-based methods, which just does the same thing every time. Maybe you could just keep the first one you generated, but then you could also do things like random tie breaking. No, your decision here can significantly impact the performance of your algorithm, but any of them are okay. So you're just going to have to decide something, and there's fun ways to do that, but we're going to be talking about that in later videos. So what's important right now, though, is that they both have the same cost. They are both ranked the same according to G of n. You can put them in either order. I'm going to keep D with 6 in first, and then I'll enter in G with 6. And finally, we have to remember that E is still around with our cost of 11. Okay, so in the following steps then, what would happen is we expand node F next. Again, I'm using a very simple example here. If there were subtrees below, it would generate its children and continue downwards. I'm just saying, hey, that these nodes here are all dead ends. They don't have any children. So the next step then is that, hey, we tried F, nothing happened. We're going to then expand D next. Nothing happens. And finally, we expand G. So your algorithm is going to terminate at the point that you expand the goal node, any goal node. So the first goal node you find and expand, well, hey, here's the lowest cost that we've found so far. We get to stop the algorithm. The other version is that, sure, maybe we have to expand all nodes in the open list in our frontier. We'd find no goal nodes, and then you could conclude there was no valid solution. But hey, we found a goal node, so we get to stop and return G with a path cost of 6. And so this is UCS. I think we can see, right, that its traversal of the tree is a little bit more chaotic than BFS. We're jumping around to completely different parts of the tree because, again, our new version, our new search strategy is going to be based solely on edge cost, and that can be highly variable and is really dependent on the original problem itself. And so similar to our previous discussion on BFS, we're now going to look at the actual properties of UCS in order to compare it against the other algorithms we've already seen and that we will see in future videos. So in talking about the properties, we talk about the main 4, which is then completeness, optimality, time and space complexity. Okay, so in terms of completeness, I think it's pretty easy to see that we will be guaranteed to find the solution if one exists. It doesn't matter where the goal is. We'll see that we will continue to expand the tree based on path cost ordering, and essentially our limit of the path cost so far of G of n is going to ever increase as we expand more of the tree, and eventually we will find G. So in this case, we do have a pretty easy yes. Now, I will though add in one more asterisk. So what I've drawn over here on the left is a easy scenario. This is where it's a properly defined problem. Here I have positive edge costs. This isn't always the case. Certain problems may have negative edge costs, as well as some actions may be essentially no ops. They might have a 0 cost. In these situations, you can end up in essentially either cycles, of which you can never escape, or you could have some form of infinite loop of no ops. So in these situations, the path cost will never be increasing, right? G of n never manages to escape out of this local minima of zeros, of no ops, which means that essentially we lose completeness in these situations. So a properly defined problem has to have essentially the minimum path cost, which we're going to call as epsilon. So epsilon has to be greater than 0 in order for the problem to be well defined. And so as part of this, the completeness can also often be restored, even in a problem with negative edge costs. So this actually just depends on how you actually structure the problem definition. So if you have the lowest negative cost is, say, an action with a cost of -10, well, what we can actually do to be smart about this and to make it a well-defined problem such that we can happily search using UCS, all we need to do is actually offset the costs by some constant amount such that the relative value of the cost is preserved, but that the epsilon, the lowest cost, is greater than 0. So if we had a -10 cost, what we could do is that we could add 11 to that cost and to all other costs, such that we shift the problem definition into something that plays nice with the behaviors of search. So that's something that's quite nice. We can also then look at optimality, right? So when we find a solution, is it the optimal solution? Is it the optimal cost every single time? I think can happily see as well that that will be true. When we're traversing the tree, the cost so far, the path cost G of n, is constantly increasing as we continue search. So the first goal node that will be found, by the time it's expanded, that will of course then have to be the lowest path cost goal that we could find. So in this case, the optimality as well is very happily yes. It is an optimal algorithm. Now, this is something that we will show a nice intuitive visual proof of in a later video as well. So now we're going to move on to the time and space complexity. Okay, so different to BFS, where we're essentially expanding right by levels, by depth. There we've described the time and space complexity in terms of the branching factor B and the depth D, the depth of the solution, right? Here though, our expansion order is not depth related, it's related to the edge costs themselves. So we're going to need to reframe the problem in order to talk about what could be the worst case number of nodes we'll have to generate and to track in terms of space, as well as then the time of expansions and things like this. So what we'd notice is that the complexity actually depends on essentially what the cost, the G of n of the solution, the optimal solution, will be. So we're going to define the cost of the optimal solution then. We'll do C star. This is just C for cost. And then whenever you have like a variable star, that often means in pathfinding terminology as well as some mathematics, this is like the optimal version, the lowest cost. So C star is the cost of the optimal solution. Cost of optimal solution. Okay? Now, instead of describing our time and space complexity then in terms of O of B to the D, where D is the depth of the solution, what it actually works out being for both of these, and I'm going to describe them essentially as, instead of O of B to the D, it's O of B to the power of 1 plus, then we have to see how many edges may we need to traverse in order to get to the cost of the optimal solution. So in the case that we have uniform costs, all the costs of the edges are just 1, then the number of steps we'll take is, instead of D, well, it will be D, but it'll also be equivalent to C star. It's the number of edges, it's the cost of the path, and the cost of the path will just be a series of 1s. In this case, the depth 2 would be equal to the cost of the optimal solution 2. However, we've just seen, of course, that we're using UCS in these problems where the costs are not uniform. So the cost, the C star of the solution here, will be 6, right? 2 plus 4. When we have this, the number of possible steps we may need to take then is going to be dependent on the smallest step size that we can make. It's dependent on this epsilon, right? It may be 1 or maybe it may be 2. The number of steps we're taking is essentially the cost of the solution divided by the smallest steps that we actually could have made. And so here we have then the cost of the optimal solution divided by epsilon. Okay, so both the space and the time complexity both come out to be this. It may look like a pretty scary math term, but I think it's pretty simple, right? It's just instead of O of B to the D, it's O of B to the how many steps we may need to take to actually reach the solution. So the next part of this is that we actually need to reason over this term in the relative size compared to b to the d. What I think is actually quite interesting to find is that O of b to the 1 plus e star over epsilon is actually going to be substantially larger than b to the d. So what we're saying is the worst case time and space complexity for UCS is going to be substantially worse than BFS. So why is this the case? Imagine that these were a series, a large number of really low-cost steps over here. Essentially, we have this massive subtree over here. The goal, of course, is over here on the right. Currently, sure, we wouldn't be reaching this, but you're going to have to consider situations where there is some prohibitive cost. Say this right subtree over here had a cost of 20 before we could continue to explore it. In this case, UCS will instead prefer to essentially exhaust all of these, this subtree as it recurses downwards for however long, until of course the path cost essentially breaches this 20 limit, and then we'll discontinue searching downwards and we'll shift over here and start exploring the right-hand subtree. But what that means is that this time and space complexity, this term here is going to grow, is often going to grow in practice substantially larger than the actual depth of the solution, because we will be exploring larger subtrees based on the path cost itself. So of course it's not always larger, but I think it's really necessary to note that this term often has a much larger worst case. So that then kind of leads us into thinking that maybe we may want to use each of the different algorithms in different situations. So an interesting point then of discussing the behavioral differences between BFS and UCS is what are the costs that we're working with in our problem. So if all costs are the same, if all costs are 1, then BFS and UCS are going to actually exhibit the exact same search behavior, right? When all the costs are the same, UCS is going to rank things just by depth, by layer, exactly the same as BFS. So what that means is that you can happily run either of them. They're both going to be complete, they're both going to be optimal. You'll be happy with either. We'll see in another exercise video that BFS will be slightly preferable in situations that have uniform costs, because we can do a little implementation trick to use our goal test at the point of generating nodes rather than expanding them. And so in that case, UCS will actually perform very slightly worse in that final depth of the solution. But essentially, for the purposes right now, you can just consider them to be both acceptable algorithms for problems where costs are the same. However, in the case that our costs are different, this is where UCS shines. And so in that case, BFS is not guaranteed to find the optimal solution, and UCS is definitely our preferred algorithm. We need to use UCS. It gives us a complete and optimal solution, and it's quite fast. So thanks for joining me here, and in the next video, we're going to continue along our fundamental search algorithms and have a look at depth first search. So see you there. Thanks.